Welcome to our next video, Systems of Linear Inequalities. In this video, we are going to continue on with our systems, but we are going to make them n equal to each other. So let's open this up to what that looks like. So we're going to start over here at the border. Now what I mean by the border is that is just referring to the line itself. So always remember that anytime you have the less than or the greater than sign, that is going to be a dotted line, or dashed is the better mathematical term. But that's going to be a dashed line of some sort. Whereas if you have the inequalities with the or equal to, that will be a solid line, because we are still sticking with the linear side of things. We are just making it to where we have something that is not equal to just one thing. There we go. Then in the shading, of course, if the variable is getting smaller or decreasing in any way, you would shade below the line, versus if it was increasing or getting greater, you would shade above the line. Perfect. And then the solutions part of this is where all points in the region by both inequalities. And essentially what I mean by that is I just want you to identify where your graphs overlap. Okay, so with equations, we typically just get one solution, or parallel lines making it no solution, or overlapping lines that make it all solutions. But it always has that equal sign, so I'm able to get a solution, versus inequalities, I'll get what's called a solution set. So we're going to do 4 different examples here. Example number 1 has y is greater than negative 2x plus 2, and y is greater than 1/3 x minus 5. So as always, your equations need to be in your y equals mx plus b form. But obviously this time we don't have the equal sign, we have the inequality sign. But the rule is still the same. You need to be able to see your slope, and you still need to be able to see your y-intercept. So I'm able to see my slope. My slope is this negative 2, because it is what's being multiplied by that variable x. So I'm going to put that as m, because m is the variable used for slope. And then we need to write this in rise over run format, because I have a graph down here. So I'm going to put that negative 2, but I'm going to put it over 1 so I can see your rise and the run. Perfect. And then with this is our y-intercept, and this is actually your starting point. So we're going to go to positive 2 on the y-axis, and then we're going to just perform our slope, down 2, 1, 2 over 1. And you can continue on with this motion until you go completely off of your grid. So that way your line is a lot more precise. That's what I've noticed with my students, is they like their line to be super precise. So I just encourage you to go all the way down. And because that inequality has the or equal to bar, that means that I can include every single ordered pair on this dotted line. So we are going to claim that as such. Now, the shading. There's a lot that goes into this, but it's actually not as difficult as it seems. So with the shading, what you have to ask yourself is, I have y, and I see that it's becoming greater. So when I look at this line here, I need my y values to continue to go upwards, because I'm going up in y values, because it says y is greater than or equal to. So what that means is at 2, I need to go up to 3, I need to go up to 4, and I need to go up into infinity. So therefore, I would shade, let me use my yellow one, I would shade above the line, just like that. By shading above the line, I'm showing that all of my y values are going to continue to increase. Versus if I had shaded below the line, it would have looked like everything was decreasing. So now you do the same thing with the other line. Plot your -5 first. Then perform your slope, up 1 over 3, up 1 over 3, down 1, left 3, down 1, 1, 2, 3. Perfect, just like that. Now I can do a precise line, but that one is just greater than, so these will be dashed. Perfect. Now the shading for this one, y is becoming greater. So when I go to my y-axis, I need to be higher than everything on that y-axis. So I'm going to shade everything above that line. Just like that. And hopefully as I'm shading, you're starting to notice that over here in, I'm going to do it in a very distinct color so that way y'all can see it. Over here in this region, this is where my graphs regions do what we call overlap. And what that does for us is it lets us know where all of the possible solutions are for these two specific inequalities. So now what they've done at the bottom here is they've given you different ordered pairs to go plot. So let's do that real quick. I've got 4, 5, so 4, 5, -3 and 1, 5, -1, and 2, -6. And what your task is to figure out which of these ordered pairs are in the shaded regions where they overlap, and pay attention to if any hit the line. In this case, none of them hit the line, so I don't need to worry about that. 4, 5 is in the combined shaded region, so that would be a solution. -3 and 1 is outside of the overlapping area, so that would not be a solution. 5, -1 is in the shaded region, therefore I can call that a solution. And 2, -6 is way under and not even in a shaded region, therefore it's not a possible solution. So that is what inequalities are asking you for in the terms of systems, is can you identify the overlapping area, can you shade correctly, and can you figure out which ordered pairs fall in those overlapping areas. Okay, I want you to pause the video and attempt to just draw the lines for example 2. Hopefully your lines look a little something like mine. So I was able to do my y-intercept at -1 and then go up 4 over 1. And then I was able to do my +4 and go down 1 over 1. Now onto the shading. We're going to shade this 4x minus 1 first, which is my brown line. And I noticed that my y values are getting greater from this point. So the only way for me to do that is to shade everything above this line. So we are going to shade, we are going to shade in this region. And then for the pinkish line, I see that y is actually getting less than, meaning that from this point I need the y values to decrease in value. So we are going to shade everything below the pink line. Just like that. There we go. And you can easily see where these graphs overlap. They overlap in this region. Just like that. So hopefully at this point you're getting a little bit more comfortable with the shading. Go plot your ordered pairs and come back. Perfect. Points are plotted. Now, I get asked this question all the times, because I've got -1, 5 here, and that hits right on this line. I get asked all the time, Miss B, can the points hit the line? Of course they can hit the line. Now, whether you claim those points or not is all dependent on the type of border that it has. This border is dashed, meaning that it does not have that or equal to that we would need to be able to actually claim that ordered pair. So because negative 1, 5 falls on a dashed line, that cannot be a solution to this system. Now, 2, negative 4 falls outside of the shaded region, therefore it would not work. 6, negative 2 on a dashed line, and it's outside of the region, therefore it would not work. Negative 5 and 3 is the only one inside the region that completely works. So don't let them trick you with that. Yes, it's on a line, however, it is not on a solid line. Okay? I want you to tip example 3. Come back when you're ready. I'm going to pause the video and completely shade and plot all the ordered pairs in the bottom. Alrighty, so hopefully your graph looks a little something like mine. Now, I know that 5/3 x minus 1 was probably a lot easier to plot. Our brains like to trick us whenever they take that variable x out. So what I hope you were able to recognize on this one is that there is actually no slope, and that is because this is in the form y is less than 4, not 4x. That is just a constant of 4, meaning that I only have a y-intercept, ooh, it looks like I didn't plot it, at the number 4. Meaning I can only hit the y-axis at the number 4. So if I were to have drawn a vertical line, that would have crossed the y-axis at every single y value. So because I only needed to hit the y-axis at 4, I was able to draw a horizontal line. Now, with the shading, y is less than or equal to, and then it gives this equation. So I have negative 1. I need all of my possible values from now on to be less than, so I'm going to shade below this line. But then I have y is less than 4, meaning that I need y's now to be also less than 4, which is why I shaded down. Now we can plot our ordered pairs. 4, negative 2, which we can see falls in the region. 6, 4, it falls in the region on a dotted line. Therefore, I cannot claim that ordered pair. 2, negative 1 is in the shaded region. Shaded region, I can choose it. And then negative 3, negative 6 falls on the line, and the line is solid. I can choose it. Okay, I challenge you to pause the video and completely work out example 4. I will come back with solutions. Perfect, hopefully yours looks a lot like mine. And of course, y is getting less than, so I go to that 3, I shade everything below. Now this one has an x is greater than 2. So notice this one had a y, I can only hit the y-axis at 4. This one has an x, I can only hit the x-axis at 2. And that line is also dashed, and x is getting larger, and x values get larger going to the right, which is why we shaded to the right. Now, the area which they were combined was this little region down here. So I've got a little bit more limited on where I can go here. Negative 5 and negative 4, obviously nowhere in that region. 2, 3, on the line, but it is dashed, therefore I cannot use it. 5, negative 1 falls on the line, but it's solid, I can claim it. And then 4, negative 6, perfectly in that shaded region. So hopefully this made solving systems with linear inequalities a lot easier. All I really need you to take away is to make sure you understand the shading process and understanding that if your point falls on a line, if it's a solid line, you can claim it. If it is a dotted line, you cannot. Alrighty, thank y'all so much. I'll see you in the next video. Bye.